In the previous video, we connected this disk drive to the Altair 680, and then we also wrote a disk utility that allowed us to fully exercise the drive, prove that everything on it worked, and that also we could control the drive from the Altair 680 with software. We're going to continue that now and try to integrate the drive fully with Altair BASIC and the assembler editor to make this machine faster and easier to use than it would be with paper tape like we saw in previous videos. Now, along those lines, if you haven't watched the previous videos in this series, I would highly recommend it, especially the video on using Altair BASIC with the teletype and using the assembler editor with the teletype, and then of course the immediately preceding video where we got this connected to begin with. As I've demonstrated in previous videos, the process of getting Altair BASIC or the assembler editor along with the program you wanted to work on loaded easily took about 45 minutes on this machine, and that's assuming you had no errors along the way, which of course with the teletype running for 45 minutes, there's a good chance you had an error or two, so quite often it took even longer than that. It's just a miserably slow, long process. In fact, it's so slow and miserable that, in my opinion, this computer just isn't even usable as a machine for running BASIC or for doing assembler editor type development. It's just too slow, and that's one of the main reasons we wanted to integrate this disk drive over here, was to speed up that process and to make that process more reliable and to be a lot quieter. Unfortunately, neither the PROM monitor, BASIC, or the assembler provided an option for loading and saving files from any other device than the console serial port. So there's no easy way for us to hook into any of these programs and point them to a disk driver we might have written, for example. However, there's another way of approaching this problem that ends up being a really good solution and in the end fairly easy to implement. If you think about it, after you've spent the 45 minutes loading BASIC or the assembler along with your program that you want to work on, everything at that point is then in RAM. And if you were to save the content of RAM at that point out to a few tracks on disk, you could get right back to that same starting point anytime you wanted by simply loading those tracks back into memory. And here's the good part. To load those tracks into memory would take just a few seconds as opposed to 45 minutes. And it would be reliable for the most part. But that's an improvement well over 500-fold. I mean, just an amazing improvement. And that alone makes this very exciting to think about. The other option here is that as you work on this program and you make changes and edits, if you were then just to write memory back out to the disk, well, you've saved everything you're doing, including any changes you've made to your source file. And that's because everything is kept in memory in these early applications. So think of it as loading and saving a workspace where the source file is just part of that, but other things are part of that as well, which comes in handy. So for example, with the assembler, you can set the end of memory address for your assembler to use down at D4, and you can set the number of nulls to send your teletype on carriage returns at CE, and BASIC has similar parameters. Or you might have patched the editor or the assembler with a bug fix. For example, it doesn't generate exclusive OR code properly, so there is a small patch you ought to make. And you make that patch, it's saved right along with the workspace, just like these other parameters. Or maybe a user function that you have in BASIC. Anything you do in memory will be saved as part of this workspace. So that can be kind of handy. And if you think about it, the program we write to load and save those workspaces is totally agnostic to what's in the workspace. So one program that we write to load and save these will work for BASIC or for the assembler editor, because it doesn't care the format of how the data is in the memory, it just needs to load and save it. And frankly, it could probably load and save pretty much any software package from this day, because at this point you were pretty much loading from paper, tape, or cassette and just running from memory. So all this looks really good. It can solve our problems quite well and be very fast. The only downside is it doesn't make really efficient use of disk space, and we'll see that in just a minute as we take a look at the source code and see how this works. So let's go ahead and cut over to that, and we'll take a look at the assembly language code for what we developed here to load and save workspaces. All right, we're going to go ahead and take a look at the code to load and save workspaces. As I mentioned, it was fairly easy to write. The main reason is because the utility we wrote in the last video gets us, 80% of the way there or so. That utility had routines for selecting drives, seeking to tracks, reading, writing sectors, and doing some console I/O. And so really all we need to do is take the main menu loop in that program where we ask the human for what to read and write, and we're just going to replace that with a loop that goes through memory and sequentially writes out all the memory or reads all the memory back in. So there's not a lot to do to make that work. The tough stuff we've already got proven out. Now, I did all this development in the assembler editor that's for this Altair 680, but as before, I did cheat a bit, and I used a modern PC with a terminal emulator, basically to give myself a 9600 baud teletype, and that made this just a little more reasonable to do. All right, so let's go ahead and take a look. I've got all this loaded. Get on this screen here. All right, so we're in the assembler editor, and I have the program in the editor, and we can type the first 22 lines of it. Oops, let me go to the beginning, and then 22 type. All right, and so this is our disk I/O routines for the Altair. And what I want you to look at first here is I have the PROM located at 7D100. So that's really not PROM on this machine, that's the upper part of RAM. So as I develop this, I'm going to run it in RAM to begin with. Once I know I like it and it all works fine, then we'll go ahead and move it into PROM. That way, we turn this machine on, we can be up and running BASIC or assembler editor all within less than 10 seconds. So it'll be a very nice setup. All right, so let's take a look at a couple of key parameters on this. Let's see, 54 lines forward. All right, so here we see some equates about the disk. This is a standard 8-inch disk with 77 tracks and 26 sectors per track. I have a parameter here called Workspace Tracks, and I currently have that set to 7. So that's how big I've made a workspace. This is a bit of a trade-off between how much memory and how much disk. So 7 divides into 77 evenly, 11 workspaces. It also gives us about 24K of RAM in each workspace, so it's a pretty good compromise. 24K is more than enough to save anything I've ever worked on in BASIC or the assembler editor. BASIC and the assembler only take about 8K themselves. That leaves a good 16K for your source program, which would be a good sized program. And note that the program can still use all 32K, we're just saving 24K of it. So your program and everything that you want to save should be in that lower 24K. Now, this also has a bit of an advantage in that it leaves 8K that's untouched by the load process or the save process. And that would be handy possibly for doing something that you want to share between workspaces. For example, let's say you had a workspace where you had a debugger. You run that debugger and it puts itself into high memory. You can then load other workspaces and run your debugger. So having that upper 8K not touched by the workspace could be something that's handy as well. All right, let's go ahead and take a look at the main loop. Let's see, I think backspace is Control A. There we go. All right, so actually here, I put a jump table in here. If you jump to the start address, you load workspace, 3 past that is save workspace. So those are the 2 main entries you would use. Now, since we have all this useful stuff in here, I went ahead and put an outside link to something that transfers an entire track. This would be good for writing a backup routine, and I'll show you that later on. Also gave hooks to the read and write sector routines and the routine in here to display a message. You might as well expose all those because they're going to be in PROM that'll be useful for other programs. All right, so now let me get to the main loop. Let's see, 33 lines forward. All right, so here's where we transfer the workspace, load or save. It's the same for either. And we start at 0 location in memory, and we're going to transfer those 7 tracks. That's what that workspace tracks is. And here you can see we transfer the track, look for an error, increment the track num, decrement the count of tracks, which will go from 7 down to 0, and repeat, and then that's it. At that point, we're done. All right, so the actual transfer track routine is going to read or write 26 sectors within that track. So let's take a look at that. So here's the actual routine where we transfer all 26 sectors in a track. Here it decides if it's doing a read or write, so it knows to jump to a write or a read. And then here I'm incrementing the sector number and then repeating. Now you can look and you can see that I'm adding 2 each time instead of 1. I do all the odd sectors first and all the even sectors second. The reason for this is because it's impossible to read consecutive sectors or write them with this disk drive. At the end of a sector, you are told, come get the data for the new sector. You then go into a loop transferring data from the controller into your program. By the time you issue the read for the next sector, the head's way over the next sector, and you will always miss it. So if you tried to ask for consecutive sectors, it would actually have a full rotation per sector. So that'd be 26 rotations. That adds up to about like 30 seconds to do a track. By doing every other sector, we can get this thing read in 2 revolutions, which is less than half a second. Now we do have step time in between that, so the whole transfer takes a bit longer. In the end, we read or write all 7 tracks in about 4 seconds. So, I mean, just a dramatic improvement. All right, so those are the main things. The rest of this is just the same sector read and write and seek routines that we had in the utility. So let's go ahead and assemble this. To do that, we go to the assembler. We'll run first pass. First pass on this only takes about 15 seconds. This is a good sized program. It would take 2 to 3 times that long in a typical CPM machine that would come along just a little bit later. So running in RAM like this is actually a very fast machine. It's nice to use. All right, now we manually run the second pass, and I'll do a listing for this. This actually is going to put it into memory at 7D100 for us, so we can then go off and execute this. And it generates a nice looking listing as it does this. It actually could assemble this faster. Most of our time here is waiting for this listing to go by. Here's the transfer workspace we looked at. Here's the transferring of a track that we looked at. Here's where I get a workspace from the user, from the screen. So here's the actual read sector. Here's our seek routines. Here's reporting an error. Here's the write sector loops, displaying a message. This is all stuff from the utility. So that's the whole thing. So let's go ahead and exit. All right, so now we're back in the monitor. Now we could try to write this off. So jump to 7D00 would be read, so 7D03 would be write. And now it's asking me to save the workspace and to give a workspace ID between 0 and A. That's 11 workspaces. Let's save this as workspace 6. Okay, that's done. It's saved the whole thing. It's saved out the disk for us. So now let's go back into the assembler. If I jump to 107, it actually erases the entire edit buffer. So you can see now it's blank. So let's go back, and now let's jump to 7D00, which is the read entry point. Load workspace 6, takes about 4 seconds. And now we'll jump back into the editor assembler, and you can see our program is here now. Super simple. Can't beat that. All right, so the next thing we'd like to do, we test this further and say it all works. Now we'd like to go ahead and put it into prom. And we can see here we're going to have to change this prom location from 7D100 to something up in prom. Where I'm going to put it is at FD100. So let's go ahead and play with this editor. You can do a change 7D00, and you hit escape to delineate the string. We'll change it to FD00 and then escape twice. And now we're on that line, so if I go 0, that'll put us at the beginning of that line, and then I can type it. And you can see it changed it to FD00. Now we have another problem, that's this opt M up here. Option M told the assembler to put it into memory as it assembled it. And it verifies that it writes it properly. If we now try to use that when we're going to FD100, which is prom space, those will all fail. So we're going to have to turn that op M off. So let's go back to the beginning, and we'll search for the opt code, sudo op I should say. And I can either comment that out or just delete it. Let's go ahead and do a change. We'll change space opt to asterisk opt. All right, so now that's commented out. So now we're not going to put it into memory, and we're running it FD100. So let's go back to the assembler now and run the first pass. So what we're going to do this time is, what we want to do is generate a paper tape so that we could send that off to Intel or MITS or somebody and have them burn a couple of 1702 EEPROMs for us. This won't quite fit in one EEPROM, but it fits in 2. And to do that, you use pass 2 with a T for a tape. Now, if I was hooked up to a teletype, this would be punching on the paper tape right now. So this is the second pass. Instead of generating a listing, it's generating the paper tape. So this I would have punched to a tape on a real teletype, and at this point I have a tape that I can go get an EEPROM burnt. All right, so let's pretend that we've sent that off and we've gotten that EEPROM burnt, and then I'll come back and put that EEPROM in, and then we'll see what this is like where we have it in EEPROM and have a machine that's up and running in no time flat. So we've assembled our workspace load save routine up at EEPROM address, and I've had the EEPROMs burned and installed them in this machine. So now we're going to see what it's like to turn on this machine and do a cold start. So we power up the Altair, go halt, reset. That's ready now. Let's turn on the disk drive, insert our disk. And now all we have to do, well, here, let's watch this. Let's watch it work. Come over here and we jump to FD00, load workspace 6. You can see the activity. And now we're up and running. And now we've loaded the workspace that had the workspace load save routines we were working on. And there they are. Simple as that. I can exit, let's see, X. And I can load anything else I wanted. So I've already done this. I've added a few other things. So let's jump to FD00 and load workspace 0. In this I have BASIC. And I've got a program in that. BASIC runs at 0. And if you look, I have the game of craps in here. So that quick, I'm up and running BASIC with a game. I won. I'm a rich man. All right, so now in BASIC, how would you get back to the monitor? Well, I can always come over here, halt the machine, reset, and then run. And then at that point, I have my prompt back. So that's one way to do it. So let's go ahead and let's load another workspace. Let's load workspace 2. This is another BASIC workspace I set up. So jump 0. And in this one, I've got the good old lunar lander program. No instructions. It's free fall for a while. And then put on some brakes. And a perfect landing. All right. So now, let's say we're not sitting right next to the Altair. Well, what you could do is put a user routine in here that just jumps to the reset vector in the prom. And that's what I've done, and it's saved right along with the workspace. So all I have to do is call the user routine. It doesn't matter what any of the parameters are, but you have to use that format. And here I am back at the prompt. All right, so another thing I did is you might want to be able to back up your disk, so it would be handy to have a backup utility. So let's see, I have that in workspace 7. So let's load that. This is an editor assembler workspace. So here is this utility to back up from drive 0 to 1. So let's go ahead. I mean, it's already assembled. Frankly, it's already in the workspace. That's, again, what's nice. I don't have to reassemble this to run it. I could just jump to it and run it. It's saved with the workspace. But let's go ahead and assemble it so you can see what it looks like. It's fairly short because I can use the routines in ROM. Whoops, that's not what I want. There's no way to, I've never figured out the backspace or delete on this assembler. Ah. All right, so here's the whole routine. Well, it's outputting. It did a combination of the listing and of the punch. Let's try it one more time. There we go. So you can see it's relatively short. Here's the start of the code, read, write, read track loop, display the messages, and exit. That's the whole routine to back up the disk. So let's go ahead and run it. I just jumped to 5,000. It says put source in drive 0, destination drive 1, asking me if I'm ready. let's go ahead and put a disk over here, back up to. And I'll type yes. And you can see it going back and forth a track at a time. Now, it's not the absolute quickest way you could do this, but it was super simple to write. It didn't take long at all because I could just call the transfer track routine in the prom monitor. And now I've got a backup routine, so I can always have backups of my disk. So here we go. We've got an extremely nice system to use now. I mean, especially if you're using a monitor instead of a teletype. I can come up from a cold start and have this machine working in just under 10 seconds, even answering all the prompts. I can run basic programs and work on them. I can run the editor assembler and develop. I can have programs in Workspaces that are ready to run. I don't have to assemble them. I can just jump to 5,000 every time I load this workspace to do a backup. And I have a utility to do a backup here. This is a very nice machine, and you don't feel how slow this 680 is for most of this. I mean, because the disk is still kind of slow compared to a lot of things in memory. And again, this is faster assembling in memory than using like a CPM system that would come along a few years later. Very nice system now. Disk makes a world of difference, and obviously it did in the marketplace too, because once disk came out, anybody who was not able to supply a disk with their system ended up really taking a beating in the marketplace, like we saw with Southwest Technical and some of those others that got behind. All right, well, that does it for this video. In the next video, I'm going to get the most popular operating system for the 6800 up and running on this machine. That was an operating system called Flex, which was essentially the CPM of the 6800 world. But we'll do that in the next video.